Recall that given integers a and b, where a is not equal to 0, the linear differential equation ax is equal to b, where x is the unknown, has a unique solution given by x star is equal to b over a if and only if a divides b. Now, since we're studying the congruence modulo, it is natural to ask, what if we replace the equality in the original linear differential equation by the equivalence under congruence modulo n? More precisely speaking, let n be a positive natural number, and consider integers a, b, where a is non-zero. The equation ax is equivalent to b modulo n, where x is the unknown, is called a linear congruence equation. In this section, we will study the solutions of such an equation. As always, our interest will be the existence and uniqueness of this equation. Under which condition will this equation has a solution? And if it has a solution, will the solution be unique? These questions can be answered by the following theorem, which states that a linear congruence equation ax is congruent to b modulo n has a solution if and only if the greatest common divisor of a and n divides b. Moreover, given the existence of the solution, we want to ask how many distinct solutions are there up to congruence modulo n. It turns out that this number is precisely GCD an. In the rest of this section, let us prove this theorem. First of all, let us study the existence. Assume that there exists an integer solution, namely u, of this linear congruence equation, which means that au is congruent to b modulo n. It is useful to translate the language of congruence modulo into divisibility, so that the statement now becomes there exists an integer u such that n divides au minus b. Again, by the definition of divisibility, this means that au minus b is equal to n times v for some integer v. Now, moving the terms concerning a and n to the left-hand side and the term b to the right-hand side, let us summarize where we are at this stage. Actually, we have obtained that there exist integers u and v such that the linear differential equation ax plus ny equals b has integer solutions given by u and negative v. Now, based on our study of linear differential equation previously, this means precisely that GCD an divides b. Since each step of inference is reversible, we have proved the existence part. Next, let us assume that our linear congruence equation indeed has a solution, and we are interested in understanding how many distinct solutions there are up to congruence modulo n. Be careful, here we are not counting the number of integer solutions. Indeed, as we have already seen, solving a linear congruence equation is equivalent to solving a linear differential equation. Now that the linear congruence equation has a solution, so does the linear differential equation. But then, the linear differential equation will have infinitely many pairs of integer solutions, which in turn implies that the linear congruence equation also has infinitely many integer solutions. Thus, if our interest is on integer solutions, clearly there will be infinitely many distinct solutions. However, in our context, we will consider two integer solutions, x1 and x2, as the same solution if they are congruent to each other. In other words, instead of counting distinct integers, we are actually counting distinct equivalence classes modulo n determined by these integers. And we claim this number is exactly the greatest common divisor of a and n. To see why this is true, let us write n is equal to GCD an multiplying some integer k. Now, assume that x0 is a particular solution of our linear congruence equation. By applying the results on the general solution of a linear differential equation, we see clearly that the form of general integer solution of our linear congruence equation is given by x is equal to x0 plus n over GCD an multiplying some integer t. That is x0 plus kt. Now, given two integer solutions, x1 and x2, we can write them as x0 plus kt1, x0 plus kt2 for integers t1 and t2. The question is, if x1 is congruent to x2 modulo n, what can we say for t1 and t2? Indeed, if x1 is congruent to x2 modulo n, then n divides x1 minus x2. In terms of t1 and t2, we see that x0 cancels with each other, and we are left with n divides k multiplying t1 minus t2. But recall that n is precisely GCD-an multiplying k. Thus, from there, we achieve that GCD-an divides t1 minus t2. In other words, x1 being congruent to x2 modulo n is equivalent to t1 being congruent to t2 modulo GCD-an. Thus, to count how many distinct integer solutions do we have up to congruence modulo n, we only need to count how many elements are there in the quotient space of integers modulo GCD-an. As we have already seen previously, this number is precisely GCD-an. This justifies our consequence concerning the multiplicity of solutions. Finally, let us illustrate this theory by looking at a simple example where we are asked to solve the linear congruence equation 6x is congruent to 2 modulo 4. Here, a is equal to 6, b is equal to 2, and n is equal to 4. We first compute the greatest common divisor of 6 and 4, which is clearly 2. Since 2 divides 2, we see that the solution exists. Moreover, since the GCD of 6 and 4 is equal to 2, we know that there are precisely 2 distinct solutions up to congruence modulo 4. Actually, direct computation shows that 1 is an integer solution of this linear congruence equation. Thus, the general solution is given by the formula 1 plus 2 times t. In other words, that is the number of all odd integers. Clearly, up to congruence modulo 4, these odd integers fall into the equivalence class determined by 1 and 3 alternatively, which justifies that there are precisely 2 distinct solutions up to congruence modulo 4.